Module 5.2 Theoretical Foundations of Phase Field. In this module, we'll discuss about the basic concept of phase field, especially order parameter, free energy functional, some of the governing equations, its numerical implementations, and also the boundary conditions. As we also discussed in the previous modules, in phase field, typically what we do is solve partial differential equations over certain domain. It was developed by J. Langer in 1978 at Carnegie Mellon University. And an important aspect of phase field is understanding interfaces of materials. So if you can remember, in density functional theory classes, we are dealing with bulk materials and so on. However, in industry and in practical applications, we encounter a lot of interface or hetero structures, which is a combination of one or multiple materials. So for that, understanding phase field becomes very important. We discussed about the order parameter, free energy functional, and also we'll discuss about the phase field variable. So what is order parameter? So order parameter are field variables that differentiate one phase from another. An example would be phases in a multi-component alloy, or broken versus unbroken phases. So you might have an alloy of 50 elements, and they might cluster together to make one phase versus other. And in order to model the interface between them, it might be important to model phase field based methods. And mathematically, these order parameters are usually denoted by this character phi, and it can range from 0 and 1. So 0 indicating one phase and 1 indicating the another phase. And an example is shown here where there is a phase on the left-hand side with phase variable 1 and the phase variable is 0. Another important concept is free energy functional. So a free energy functional is the total free energy of the system expressed as a functional. So a functional is a function of a function of the order parameter and its gradients. So we discussed about density functional theory. So in that case as well, we had a function of density. So that's why we had functional. And here, in a way, phase field can also be considered as density functional theory based method, or density functional theory based method can be considered as a phase field method because they also deal with functional. And the order parameter in this case could not just be only density, but other forms of mathematical objects such as the cracks, or it could be the one phase versus another. So generally, free energy functional is denoted as a function of phi, and this phi has f phi and the Laplacian of phi squared integrate over the volume V. So the phi is the order parameter, f phi is a local free energy density, kappa is the gradient energy coefficient, and Laplacian of phi is gradient order parameter, and V is the volume. So in general, what we're trying to achieve is get the minimum of f, because there's such a complicated, it could be such a complicated function. Knowing its minimum analytically is very difficult task. That's why we need to employ numerical methods. And this directly follows the second laws of thermodynamics, just for entropy reasons. An example could be when you throw a ball in the sky, it always want to minimize its energy by coming down to the land or earth. But we want to do something similar for our phase system as well. So we discussed the bulk free energy and the gradient free energies. And bulk free energy kind of describes the energy associated with a local system, so A versus B, and gradient energy is penalizes spatial variation in the order parameter to ensure smooth transition, for example, from A to B. So that the gradient part is also important, not just the bulk part. There are two main governing equations in phase field, Allen-Kahn equation and Kahn-Hilliard equations. So in Allen-Kahn, we are dealing with non-conservative dynamics. Remember, we are still conserving energy and basics laws of physics are not being violated, but we have freedom to have non-conservative order parameter, non-conservative dynamics, and it can describe the motion of phase boundary or interface between different phases, with L as a mobility parameter, which is usually obtained from experiments or molecular dynamics simulation. This is used where order parameter can change locally without being conserved globally, such as grain growth. When you have one small grain taking place and this grain can keep growing and so on, and in that case, the order parameter may not be conserved. The equation for Allen-Cahn equation is given below, where we have the rate of change of the order parameter del phi over del t is given by the mobility parameter L and the gradient of the free energy, that is del F over del phi. And this can also be represented by minus L del F phi over del d phi and kappa of Laplacian of phi. So that's just the functional form we learned in the previous slide. Now, there could be another impression called Cahn-Hilliard equation. So this is especially useful for conservative dynamics. That is, the total amount of the order parameter remains constant. This is usually employed for diffusion controlled processes such as the phase separation, and it can be denoted by a fourth order derivative. You can consider as m is the mobility coefficient, and which is obtained from the experiment or molecular dynamic simulations. And you can see the rate of change of the order parameter have two Laplacian term, and the mu is the chemical potential, usually given by the derivative of the free energy over the order parameter. We'll learn about comparing them in the hands-on session. So when we try to apply these equations for solving a real-life problem, we might have to learn about a concept called discretization. And discretization, it involves breaking down a continuous problem into discrete part for numerical analysis. And usually we can convert a partial differential equation into algebraic equation, and then we can solve it. And there are many methods for this computational methods. There could be finite difference, finite element, finite volume, spectral method. Especially, we'll be using finite difference method. We also saw that example in the mathematical and programming basics in the first module. So we'll stick to this. And in the next continuum mechanics module, we'll learn more about the finite element method as well. So let's briefly talk about these methods. So finite difference method, it approximates derivatives using difference between function value at the grid points. So you can have spatial discretization such as the first order derivative, where we have the derivative of phi with respect to the x domain. So phi I plus 1, the value of the order parameter at the grid I plus 1 and order of the value of the order parameter at grid I minus 1 divided by the 2 and the length or the width of the interval. Similarly, we can get the second order derivative. To have the temporal discretization, we can have a similar idea where the n plus 1th level order parameter is given by the nth level and the discretization interval delta t and the gradient or the order parameter with respect to time. So this advantage is pretty simple to implement. You will see that in the numerical examples. And however, there are a lot of disadvantages of this method, such as dealing with complex geometries, especially when you have not just a grid of n by n geometry, but also very sharp shapes and so on. We'll see the finite element case. Now, in the finite element case, we are dealing with smaller elements, and we want to use piecewise polynomial functions to approximate these solutions. An important concept in finite element method, which we'll also learn in the next module, is how to convert a strong partial differential equation into a weak form by integrating against a test function. So this test function becomes extremely important, and especially when we are using irregular domains, the finite element method could be quite useful. And discretization in basis function, we have the way to approximate the solution within each element, so especially for complex geometry, and assemble the global system equation from the elemental contributions. it has extremely advantageous feature of dealing with complex geometry and boundary conditions, and it's very highly accuracy can be achieved with adaptive mesh refinement methods. However, there are disadvantages, such as it can be, as you can kind of guess, it can become computationally quite intensive for larger problems. So here's an example of solving a Poisson equation with where we multiply the Poisson equation with a test function v, and then if you remember the integration by parts in calculus, we can kind of break it down, the second equation, into third, assuming the test function derivative is small. So there's a small derivation there. We'll try to go through that in the finite element continuum mechanics course, but just an introduction. Another similar approach is finite volume method. So you can kind of guess, instead of dealing with elements, we are dealing with volumes. And it ensures the conservation of quantities such as mass and energies, and is typically used for computational fluid dynamics. We'll touch upon that as well. And in this FVM, the typical elements are polygon or polyhedrons. And the guiding principle of FVM in the previous case was weak formulation. Here in FVM is conservation of fluxes. The advantages are, first, naturally it conserves the quantities, so we don't have to kind of enforce too many things. It naturally conserves them. It is highly flexible for unstructured meshes, and very robust for discontinuities and sharp gradients. Challenges are, as you can imagine, it can be computationally very expensive, and imposing boundary conditions for volume elements can be quite non-trivial. Another less used but still very interesting method is spectral method. So in spectral methods, we want to approximate the solution using global basis function, which typically involves trigonometric polynomials or orthogonal polynomials with sine and cosines. So the discretization is performed using transforming the partial differential equation into a spectral space using Fourier or Chebyshev polynomials. And the advantage is very smooth because you use the sine and cosine functions. But the disadvantage is when you are trying to deal with sharp gradients, the sine and cosine function based method may not be very reasonable. Important concept to learn here is boundary conditions. We discussed about that a little bit earlier as well, but let's deal with some of the different types of boundary conditions. So boundary condition is very important, and they specify the behavior of the solution at the boundary of the computational domain. For example, if you have a beam, you might want to fix the beam on one side and you want to apply the load on another side. So you might have to apply the boundary conditions appropriately. It can realistically and physically model the simulation parameters, and there are different types of boundary condition. There can be Dirichlet type, Neumann type boundary conditions, or mixed type boundary conditions. So in Dirichlet type, you can see it specify the value of the phase field variable on the boundary, and it's given by phi equals to phi 0 on the domain. However, the Neumann, we just not just fix the phi, but also the gradient of phi is kind of specified. And in the mixed boundary condition, as you can imagine, we have both the phi and the del of phi is as the conditions applied. And the applications are quite trivial. When we want to fix the initial phase and have solid walls, then Dirichlet boundary conditions are good. But if you want to control the flux or the rate of change of the field variable, then you might have to apply Neumann. And for complex boundary conditions where we have multiple objects, some are fixed, some are flux-based, then you have to apply mixed boundary condition. For implementation, Dirichlet boundary conditions are directly applied for nodes in the FEM, the Neumann for stiffness matrices and force vector, and Robin or mixed-based boundary conditions can be used where we have combination of both of these. So I want to point out in the DFT and coarse graining and molecular dynamics and so on, we learned about various softwares. We learned about DFT in software as GPaw, VASP, Quantum Espresso. We learned in MD, the software as LAMMPS, and coarse graining, we learned about LAMMPS, GROMACS, and so on. However, in phase fill, there is not such a unified package because It mainly deals with solving partial differential equation. So there are many softwares which can be in principle for applied for solving finite element uh, phase field kind of models. So these are MOOS, Phoenix, PhyPy, Prism PF, OpenPhase, and then commercial package Micres. So we'll be touching upon PhyPy and maybe Phoenix a little bit during the tutorial. And we also deal with some of the NumPy-based toy problems in the next module to understand and have a grasp on phase field models.